silence, the universe emerges not as chaos, but as order written in symbols. From Newton's apple to Einstein's stars, reality seemed to reveal itself in numbers. Gravity was not a mystery, was a formula. The paths of planets, the tides of oceans, the flight of comets, all could be traced with precision. Mathematics appeared as the very skeleton of nature, a cathedral of logic holding the cosmos upright. But even cathedrals have cracks. There are places where the language of mathematics falters, where equations so perfect, into nonsense. A black hole, for instance, the heart of a collapsed star, where density grows without limit. At its center lies a singularity, a point where space and time themselves are twisted into infinity. There Einstein's equations do not yield answers. They scream in contradictions. Or consider the Big Bang. Cosmology traces everything back to a beginning, an origin of matter and energy. Yet, at the very first instant, at time zero, the formulas that once described the universe refuse to work. Infinity again. A horizon of unknowability. The void reveals itself not as emptiness, but as a fracture lantern, but a shadow. What lies beyond? Are these infinities real, stitched into the fab line in human reason? It is a boundary where thought dissolves, where mathematics is no longer aric of being. Or are they warning signs, telling us our equations are only temporary scaffolds, fragile, bridges over a truth too vast to calculate? Humanity once believed the universe was unknowably, till mathematics brought order. Now, as it peers into black holes and the origin of time, it faces a new terror, that order itself may have limits, that beyond the void, no equation can follow. For most of human history, the universe seemed incomprehensible, a stage ruled by gods, chance, or chaos. The motion of stars was mysterious, the fall of stones inexplicable, the tides divine. Time was kept with shadows and seasons, yet no deeper law was understood. But then, a revolution arrived, not of temples, but of numbers. In the 17th century, Isaac Newton stood beneath an apple tree and imagined the heavens bending to the same force that pulled fruit to the ground. With a stroke of genius, he wrote gravity as mathematics. The orbits of planets, once traced by the careful observations of Kepler, became the solutions to his equations. The cosmos, once filled with mystery, now appeared as a machine of clockwork, whose gears were calculus, whose rhythm was predictable. Newton's laws revealed a universe not of chaos, but of order. The dream deepened in the 19th century with James Clerk Maxwell. He wove electricity and magnetism into a single tapestry, revealing that light itself was an electromagnetic wave. Once again, equations revealed. Unity phenomena, once thought separate, emerged as facets of one law. It seemed that nothing in the natural world lay beyond the reach of mathematics. From falling stones to the speed of light, reality could be written down. And then came Einstein in 1915. His general theory of relativity transformed the very notion of space and time. The universe was no longer a rigid stage, but a fabric, curved and bent by matter and energy. Planets moved not by invisible pulls, but by following the contours of spacetime itself. Relativity was hailed as the ultimate triumph of mathematics, an elegant geometry describing the largest structures of reality. But hidden in Einstein's equations was a dark implication. In 1916, Karl Schwarzschild, a German physicist serving on the front lines of World War I, found an exact solution to Einstein's field equations. It described what would later be called a black hole, a region where gravity becomes so extreme that not even light can escape. And at its heart, the mathematics predicted something unimaginably: singularity, a point of infinite density where space-time collapses. Here, for the first time, the equations revealed not order, but their own undoing. At first, physicists resisted. The idea of singularities seemed absurd, an artifact of mathematics pushed too far. Einstein himself doubted that nature could permit such monstrosities. He trusted his equations, but distrusted the infinities they implied. And yet, the mathematics returned again and again. In the 1920s, Alexander Friedmann and Georges Lemaitre studied Einstein's equations not for collapsed stars, but for the universe as a whole. They discovered that the equations did not describe a static cosmos, as Einstein had hoped, but one that was expanding. And if the universe was expanding, it must once have been smaller, denser, compressed into a singular beginning. The Big Bang was born, another singularity, another point where equations ceased to work. Still, for decades, these infinities remained theoretical shadows. No telescope could see them, no detector could measure them. They seemed like curiosities, perhaps even errors. But in 1965, the heavens themselves answered. Arno, Penzias, and Robert Wilson, working with a radio antenna in New Jersey, stumbled upon a faint hum, a background of microwaves that came from every direction in the sky. It was not noise. It was the afterglow of creation itself, the cosmic microwave background, a fossil light from when the universe was only 380,000 years old. This discovery confirmed the Big Bang theory and anchored cosmology in observation. Yet it also sharpened the question: if the universe truly began in a singularity, what came before? Meanwhile, in the realm of stellar death, evidence mounted that black holes were not merely mathematical curiosities, but astrophysical realities. In the 1960s, astronomers discovered quasars, distant, brilliant beacons powered by matter spiraling into supermassive black holes. In the 1970s, Cygnus X1, an invisible companion devouring its star, became the first strong candidate for a stellar black hole. Singularities were no longer abstractions. They were real, written in the sky. By the 1970s, Stephen Hawking and Roger Penrose sharpened the picture. They proved mathematically that singularities were not optional oddities. They were inevitable, the natural consequence of Einstein's relativity. If a star collapsed beyond a certain point, or if the universe expanded backward in time, singularities would form. The equations themselves guaranteed it. But what is a singularity? At its core, it is not an object, but a failure. It is the place where density climbs to infinity, where curvature becomes unbounded, where time itself ceases to flow in any ordinary sense. It is where the language of physics breaks. To divide by zero is trivial nonsense on paper. A singularity is dividing by zero written into the cosmos itself. The early triumphs of mathematics, the precise orbits, the elegant fields, the geometry of space-time had led to an astonishing revelation. The universe was not just calculable, it was willing to reveal itself. Yet now it revealed something darker. The same equations that once promised infinite comprehension were pointing to their own limitations. Black holes, the Big Bang, two sides of the same mystery, two singularities, where the cathedral of mathematics crumbles into silence. The implications unsettled the scientific imagination. If the very equations that had guided humanity from apples to galaxies collapsed at the most extreme edges of reality, then perhaps they were not final truths, but approximations, temporary scaffolding pointing to something deeper. And so, the discovery phase ends in paradox. The cosmos, once illuminated by equations, now seemed to whisper of a void where equations fail. The singularities of black holes and the birth of the universe were not merely curiosities, they were cracks in the foundation, signs that mathematics, for all its triumphs, had limits. The clockwork dream of Newton was broken. The geometric vision of Einstein had revealed its own blind spot. Humanity stood on the threshold of a terrifying realization that beyond the void, numbers may lose their meaning, and the universe may not be written in equations at all. There is a peculiar kind of terror in mathematics, not the terror of violence or of night, but of infinity. For centuries, equations were the lanterns guiding human thought through the dark. They measured the stars, explained the tides, mapped the hidden paths of planets. They promised certainty. Yet in the middle of the 20th century, that certainty cracked open, revealing a darker landscape, the places where mathematics itself dissolved. These places were called singularities. In the equations of general relativity, singularities arose naturally. They were points where spacetime curvature became infinite, where density collapsed into zero volume. They were not exotic features added by hand, but the inevitable products of Einstein's beautiful mathematics. But this beauty hid a wound. Infinities in equations are not physical predictions. They are breakdowns. They are where the language ceases to describe reality. At first, even Einstein resisted. He distrusted the idea that nature could contain infinities. His universe was orderly, calculable, geometric. The notion of black hole stars collapsing into singularities seemed absurd to him. He believed something in physics must intervene before such collapse could be complete. God does not play dice, he once said of quantum mechanics, but he might just as well have said, God does not make infinitises, but the mathematics would not relent. By the 1960s, Roger Penrose and Stephen Hawking brought rigor to the nightmare. They developed the singularity theorems, proving that under broad and realistic conditions, singularities were not optional, they were unavoidable. If relativity was true, then singularities must exist. The collapse of massive stars could not be halted. The birth of the universe itself implied an origin of infinite density. This was the shock. The very equations that had once mapped the cosmos now predicted their own demise. Imagine dividing by zero on a chalkboard. The line of reasoning halts, logic breaks. Now imagine that this breakdown is not a mistake, but written into the laws of nature, that is the singularity. A place where prediction ends, where causality collapses, where time itself may have no meaning. The shock deepened when quantum mechanics entered the frame. In the quantum world, particles dance in probabilities, governed by equations that never allow infinities. Yet, at singularities, quantum rules also fractured. Probability itself seemed to vanish. No framework classical or quantum could survive. Hawking pushed further, considering the paradox of black holes. In 1974, he showed that quantum effects near the event horizon would allow black holes to emit faint radiation, now called Hawking radiation. Black holes, once thought eternal, could evaporate. But this prediction led to another singular breakdown, the black hole information paradox. If a black hole evaporated entirely, what happened to the information about everything it had consumed? Quantum mechanics insists information is never destroyed. Relativity, through black holes, suggested it could be. Two of the greatest frameworks in science were colliding, each denying the other at the edge of the singularity. It was not only black holes. The Big Bang itself posed an even greater challenge. If the universe began at a singularity, then what preceded it? Was there a before time began? Or was the beginning itself a meaningless concept? Relativity could not say. At the Big Bang, equations reached infinite density and collapsed into nonsense. Scientists looked again at the equations of cosmology, the Friedmann equations, derived from Einstein's relativity, described an expanding universe with extraordinary precision. Yet, when extended backward, they demanded a singular beginning. They carried within them the seeds of their own destruction. The shock of this was profound. Humanity had believed, since Newton, that mathematics was a mirror of reality. Yet here, at the most fundamental edges, the mirror shattered. The singularity was not a window into truth, it was a wall, and the wall was not hidden far away. It was at the center of every black hole, at the birth of every galaxy, at the beginning of time itself. The void was not peripheral, it was central. The reaction among scientists oscillated between fascination and dread. To some, the infinities were clues, signposts pointing to new physics. To others, they were dead ends, warnings that the language of relativity had been pushed too far. But either way, they could not be ignored. The shock also carried a philosophical weight. If equations could fail, what did that mean for the dream of science? Could reality itself be beyond numbers? Was mathematics only an approximation, a human attempt to capture truths that ultimately defy capture? Stephen Hawking once remarked, "The greatest enemy of knowledge is not ignorance, it is the illusion of knowledge." Singularities exposed that illusion. They revealed that even the most elegant theories could falter. That infinity, far from being an abstract idea, haunted the fabric of reality. There is a peculiar silence in the face of infinities. Astronomers who peered into the centers of galaxies, physicists who calculated the birth of the universe, all encountered the same abyss. It was not chaos, but a kind of void, structured, inevitable, and yet beyond comprehension. Here, in the singularities of black holes and the origin of the cosmos, equations ceased to work. And with that failure, humanity glimpsed something terrifying, that science itself had boundaries, that there were places where mathematics, the very language of order, could not follow. The scientific shock of singularities was not merely that infinities exist. It was that infinities exist within the laws we trust most. General relativity, the most beautiful and precise description of gravity, carried within it the seed of its own unraveling. Quantum mechanics, the most successful framework of the microscopic world, collided head-on with relativity at the singularity. Two triumphs became two contradictions, locked in a paradox with no resolution. The void revealed itself not as absence, but as a wound in knowledge, a place where the two great empires of modern physics, relativity and quantum mechanics, met, only to deny one another. And so the shock lingers. For scientists, it is a call to arms, to seek a deeper framework, a quantum theory of gravity that could reconcile the contradictions and heal the infinities. For philosophers, it is a reminder of humility, that even the most trusted equations may falter at the edges of truth. The singularity stands as a monument to both triumph and failure, proof of how far equations can reach, and a boundary showing where they cannot. It is the sharp edge of knowledge, the line where science peers into the void and finds not clarity, but silence. In that silence lies both terror and promise. For if equations fail, then beyond them must lie something else, something waiting to be discovered. The shock of singularities left a wound in physics, but wounds often become the sites of the deepest inquiry. If equations failed at the centers of black holes and at the birth of the universe, then perhaps those failures contained clues. The void was not simply a limit, it was an invitation. In the decades after Einstein, the investigation deepened. Telescopes, satellites, detectors, and supercomputers were turned toward the places where equations faltered. Scientists began to probe not only the skies but the very structure of space-time itself, and in doing so, they discovered that the void was not empty, it was alive with signals, with whispers, with strange geometries hinting at a deeper truth. The first great battlefield was the black hole. When Carl Schwarzschild first solved Einstein's equations in 1916, his solution suggested an object of immense gravity. A star collapsed so completely that even light could not escape. At its center, a singularity. At its edge, an event horizon. For decades, this solution was dismissed as a curiosity, a strange mathematical ghost. But by the mid-20th century, the ghosts became real. Astronomers discovered Cygnus X1, a binary system where one invisible companion pulled on its partner with unseen mass. No ordinary star could explain it. Only a collapsed giant black hole fit the data. What had once been unthinkable became observable. And with that observation, singularities could no longer be ignored. The investigation accelerated. Radio telescopes mapped the cores of galaxies, revealing jets of matter fired at near light speed from invisible centers. The only engines powerful enough to launch such torrents were supermassive black holes, millions, even billions of times the sun's mass. At the heart of our own Milky Way, Sagittarius A** betrayed itself by the rapid dance of nearby stars, orbiting something dark, something immense, something that equations said must hide a singularity. Still, the singularity remained hidden behind its horizon. The void was real, but unseen. Then, in 2019, the Event Horizon Telescope offered humanity its first image, a shadow cast against glowing matter, the outline of a black hole in the galaxy M87. It was not a direct glimpse of the singularity, but it was a silhouette of the abyss. For the first time, humanity had proof not only in numbers but in sight. The void was real, yet black holes were not the only windows. The entire cosmos offered another. In 1965, Arno Penzias and Robert Wilson, while calibrating a radio antenna in New Jersey, stumbled upon a faint, persistent noise. It came from every direction, uniform across the sky. At first, they thought it was pigeon droppings inside the antenna. But after they cleaned it, the noise remained. It was no local interference, it was the echo of creation itself. This radiation, now called the cosmic microwave background, was the afterglow of the Big Bang, a fossil light from when the universe was only 380,000 years old. In it lay patterns, tiny ripples in temperature, differences of only 1 part in 100,000. Yet these ripples carried the memory of something deeper. Fluctuations stretched across the cosmos by the inflationary expansion that occurred fractions of a second after the Big Bang. Satellites, like COBE in the 1990s, WMAP in the 2000s, and Planck in the 2010s, mapped the microwave background with exquisite precision. Each mission revealed a sky patterned not in chaos but in order and isotropes that spoke of a primordial rhythm. These were not singularities, but signatures of them, traces of the physics that equations could not yet describe. The investigation reached further. Physicists examined baryon, acoustic oscillations, fossilized sound waves from the early universe, ripples of pressure frozen into the distribution of galaxies. They were the heartbeat of creation, each oscillation a tick of a clock that might predate the universe itself. By measuring these, cosmologists traced not only the expansion of the universe, but also the hidden structure of its birth. Meanwhile, theorists turned to quantum field theory. At the smallest scales, the vacuum itself, seethed with fluctuations. Particles appeared and vanished, energy bubbled out of nothing, only to return. This framework, designed to tame infinities, worked with astonishing success, predicting particle behavior to more than 10 decimal places. And yet, when merged with gravity, it failed. Attempts to calculate the energy of the vacuum produced results 120 orders of magnitude larger than what was observed in cosmic acceleration. A failure so vast it was called the worst prediction in physics. The void, it seemed, mocked every attempt to capture it. Physicists searched for reconciliation. They dreamed of a quantum theory of gravity, one that could marry relativity with quantum mechanics, curing the infinities of singularities. String theory proposed that particles were not points but vibrating strings, their oscillations smoothing spacetime into harmony. Loop quantum gravity suggested that spacetime itself was discrete, woven from tiny loops that dissolved singularities into granular geometry. The holographic principle imagined the universe as a projection, its true description encoded on low boundaries. Each idea was bold, each elegant, and yet none fully proven. Experiments pressed against the limits of what was possible. Particle colliders, like CERN's Large Hadron Collider, smashed protons together at near-light speeds, searching for glimpses of new physics. Underground detectors strained to catch whispers of dark matter, particles invisible yet gravitationally. Essential quantum laboratories cooled atoms to near absolute zero, crafting Bose-Einstein condensates to simulate horizons, hoping to glimpse analogues of Hawking radiation in the laboratory. Every path returned to the same riddle. Singularities were not errors to be discarded. They were signals. They marked the places where current knowledge broke, the gateways to something beyond. Even supercomputers joined the quest. They simulated the collapse of stars, the dynamics of black hole mergers, the fluctuations of the infant universe. They modeled conditions near singularities with unprecedented detail. And yet, even in the digital cosmos, infinities reared their heads. The simulations halted, the equations diverged. The void appeared even inside the machines built to chase it. And so, the deeper investigation revealed a paradox. The more evidence gathered, the more real singularities became. Black holes existed. The cosmic microwave background was mapped. Gravitational waves were detected, ripples in spacetime confirming relativity's deepest predictions. Every experiment confirmed the frameworks that led to singularities, yet the singularities themselves remained places where those frameworks failed. It was as though the universe were pointing insistently toward a truth beyond mathematics, whispering that current equations were only scaffolding, not the foundation. The void where equations ceased to work was not a distant abstraction, it was woven into the universe's story. From its first moments to its darkest depths, what began as shock became pursuit. Singularities were no longer ghosts. They were compasses, and in following them, humanity found itself at the edge of knowledge, peering into a darkness that was not empty, but alive with possibility. The deeper humanity looked, the more the mystery grew. Singularities were not erased by new data, they were sharpened. Black holes, once dismissed as curiosities, became cornerstones of astrophysics. The Big Bang, once debated, became undeniable, and yet, in both equations crumbled. With every confirmation of their existence, the weight of their paradox grew heavier. The void was no longer distant, it pressed against the very fabric of knowledge. The escalation began with certainty itself. Relativity had triumphed. Its predictions had guided spacecraft, explained Mercury's orbit, bent starlight around the sun, and mapped the warping of spacetime by mass. Its equations were smooth, elegant, inevitable. Yet those same equations led directly into singularities. Stephen Hawking and Roger Penrose proved it with mathematical precision. If relativity were true, then singularities were unavoidable. There was no escaping them. Collapse a star beyond a certain threshold, and space-time itself would collapse into a point. Run the expansion of the universe backward, and all of creation ended in an origin of infinite density. Relativity, the most successful theory of gravity ever written, carried within it the seed of its own undoing. The very tool used to measure reality was admitting its own failure. The crisis deepened with the discovery of Hawking radiation. By applying quantum mechanics to black holes, Hawking found that event horizons were not absolute. Virtual particles, flickering into existence at the boundary of a black hole, could steal energy, leading to a slow evaporation. This elegant calculation carried an unbearable consequence. If black holes evaporated, what became of the information inside? Quantum mechanics declared information could never be destroyed. Relativity declared that black holes swallowed it forever. Hawking's radiation made the contradiction unavoidable. Information would vanish into nothingness as the whole evaporated. Outcome forbidden by quantum law. This became the black hole information paradox. At its heart lay not a quibble of calculation, but the collision of two pillars of physics, relativity and quantum mechanics, the two great frameworks of the 20th century, could not both be true in the presence of a singularity. The void where equations ceased to work was not an exotic location in space. It was the junction where reality itself fractured. The paradox spread beyond black holes. In the realm of cosmology, singularities threatened the beginning of time. The Friedman equations, which described the expanding universe, traced backward to a singularity. Yet quantum cosmology suggested that perhaps time itself dissolved there, replaced with probabilities, with quantum foam. The beginning was not a moment, but a breakdown. A place where mathematics whispered of possibilities it could not describe. Even worse, dark energy entered the scene. In the late 1990s, astronomers measuring distant supernova discovered that the universe's expansion was accelerating. Something unseen, something woven into the vacuum, was pushing galaxies apart. When theorists tried to calculate the energy of the vacuum with quantum field theory, the result was catastrophic: 10 to the power of 120 times larger than observed, a number so vast it defied comprehension. This was not simply a mismatch of measurement. It was a collapse of reasoning, another singularity of knowledge, erupting not in black holes but in the equations of the cosmos itself. Dark energy revealed that the void was not only at the beginning or the centers of collapse. It was everywhere. Every cubic centimeter of space seemed to carry this mysterious energy, and yet equations could not capture it. A universe filled with a present science could not explain. An omnipresent reminder that equations might not tell the full story. The escalation grew darker with the question of naked singularities. According to relativity, singularities should remain hidden behind event horizons, shielded from the external universe. This was the cosmic censorship conjecture nature's supposed safeguard, cloaking infinities from view. But if cosmic censorship failed, if a singularity were laid bare to the universe, then the laws of physics would fail not in hidden corners but in the open sky. Time itself could unravel, causality could break. The future could dissolve into unpredictability. The threat was not confined to thought experiments. Rotating black holes, described by the Kerr solution, suggested pathways through their centers, possibly revealing singularities Were they hidden or exposed? The equations did not agree. The possibility loomed that the universe itself might expose its naked eye in laboratories of thought. The danger spread further still. If singularities could be traversed, if equations broke open into other regions, then perhaps black holes were not ends but bridges. Wormholes, tunnels to other universes might form where mathematics collapsed. But if so, they were bridges not built by physics, but carved from its failure. Were they stable, or would they consume themselves, collapsing into chaos? The equations offered no certainty. The escalation reached its most haunting form in the realm of entropy. The second law of thermodynamics declared that entropy always increases, that disorder always grows. Yet singularities seemed to defy this rhythm. The Big Bang began in low entropy, improbably ordered. Black holes swallowed matter and erased information, threatening to decrease entropy in ways forbidden by physics. At every turn, the void pressed against the most fundamental principles of order. The dread was not merely theoretical. In every singularity lay the possibility that reality itself was fragile, that the laws that made fire burn and planets orbit and light bend could, under pressure, dissolve into nonsense. The void where equations ceased to work was not a remote anomaly. It was a fault line running beneath all of science. And so the mystery deepened. Singularities were not going away. They were multiplying. They were appearing in black holes, in the beginning of the universe, in the vacuum energy that filled all of space, in the entropy of the cosmos itself. Every path into the deep revealed new fractures. Physics had once promised certainty that nature could be written in equations, complete and final. But with every new discovery, the promise eroded. The universe seemed to insist otherwise, that beyond a certain point, no equation could reach. That at the deepest level, the map of mathematics ended, and a territory of mystery began. The escalation had transformed singularities from curiosities into the central threat of modern physics. They were not edge cases, but hard cases. They challenged relativity, quantum mechanics, thermodynamics, cosmology. They revealed that the frameworks of science, once thought unshakable, were incomplete, and so humanity found itself in a place of awe and fear. Equations still guided spacecraft, still mapped galaxies, still unlocked technologies. But beyond, in the void, equations collapsed. It was as though the universe whispered, "Here is the limit of what you know. Beyond this, you must imagine. Beyond this, you must invent." The void was no longer distant. It was the mirror of science itself, reflecting not only what was known, but the places where knowledge fell silent. And in that silence, the greatest mystery deepened. The void where equations collapse is not merely an abyss to be feared. It is also a canvas, a place where imagination, sharpened by mathematics, is called upon to paint the outlines of truths not yet seen. For when old equations fail, new ones must be written. When infinities erupt, science seeks patterns that dissolve them into meaning. And so the void becomes a crucible of speculation, a chamber where theories compete to explain what lies beyond the collapse. The first and most audacious contender is string theory. In this vision, particles are not points, but tiny vibrating strings, oscillating in dimensions far smaller than an atom. To our senses, they appear as electrons, quarks, and photons, but in truth, they are musical notes on a cosmic instrument. Where relativity predicts singularities, string theory softens them. The infinite density of a black hole core is replaced by a finite, vibrating knot of strings. The instant of the Big Bang becomes not a singularity, but a transformation of strings from one state to another. The harsh infinities are replaced with smooth geometry. Yet, though elegant, string theory remains untested. Its extra dimensions, curled into spaces smaller than any microscope can see, leave little trace in experiments. It whispers of resolution, but does not yet deliver proof. Another approach takes the form of loop quantum gravity. Here, spacetime itself is not smooth, but woven from discrete loops, tiny quanta of geometry. Just as matter is made of atoms, spacetime is made of indivisible grains. At the Planck scale, far smaller than any proton, time and space cease to be continuous. Singularities dissolve into bouncing structures. A black hole core, instead of collapsing to infinity, rebounds into a new region of spacetime. The Big Bang is not the beginning, but a bounce from a prior universe. In this picture, the void where equations fail becomes a bridge. Connecting cycles of creation, then comes Hawking's no-boundary proposal. With James Hartle, Hawking suggested that the Big Bang singularity might be an illusion. Instead of a sharp beginning, time near the origin curves smoothly, like the surface of the Earth near the South Pole. There is no edge, no singular moment. Time simply rounds off, finite but without boundary. In this vision, the void where equations collapse is healed not by new physics, but by geometry itself, bending seamlessly into something beyond comprehension. Still others turn to the holographic principle, an idea born from the black hole information paradox. If information cannot be destroyed, then perhaps the true description of the universe is not inside the void, but on its boundary. Just as a hologram encodes a three-dimensional image on a two-dimensional surface, perhaps all of space-time is encoded on a cosmic horizon. In this framework, singularities do not exist as points within space. They are artifacts of a projection. The true laws lie deeper. In quantum information inscribed at the edge of reality, speculations also touch the most dangerous possibilities, false vacuum decay. In quantum field theory, our universe might not be in its most stable state. It may rest in a false vacuum, a fragile plateau of energy. If so, it could tunnel to a lower state, unleashing a bubble of destruction that expands at the speed of light, rewriting physics as it passes. In this chilling scenario, the void is not confined to black holes or the Big Bang. It could emerge anywhere, erasing equations, not by collapse, but by replacement. Reality itself could dissolve, its laws rewritten in an instant. Even more expansive are the ideas of the multiverse. Eternal inflation suggests that our universe is one bubble among countless others, each with its own physics. What we call singularities, big bangs, black holes may be portals to these other domains. In this view, the void where equations fail is simply the crossing point between universes, a seam in the infinite quilt of existence. Each bubble follows its own equations, but none are ultimate. Mathematics itself becomes local, fragile, contextual. The heart of these speculations lies a philosophical tension. Are infinities real features of the universe? Or are they warnings, signposts marking where our equations have reached their limits? Many physicists believe the latter, that infinity is not physical, but a failure of language. In this view, singularities are not objects in the cosmos, but mirrors, reflecting our incomplete understanding, and yet there are whispers of something deeper still. Some argue that time itself is emergent, that the ticking of clocks and the flowing of seconds are not fundamental, but arise from entanglement, from correlations in quantum states. In this radical vision, the void where equations collapse may not be a failure, but a clue, a hint that time is not woven into the universe at its core, but rises like steam from the interactions of deeper laws. If so, singularities might not be places where time ends, but where time has not yet emerged. Others ask whether mathematics itself is the limit. For centuries, humanity has trusted equations to reveal truth. But what if reality is not mathematical at its deepest level? What if equations are shadows, projections of a structure that transcends numbers? Some philosophers whisper of informational or logical foundations, where bits, not numbers, form the bedrock. If so, the void where equations cease to work is not a failure, but a doorway to a reality beyond mathematics. The spectrum of speculation is vast, from strings vibrating in 11 dimensions to loops of quantum geometry, from holograms at the edge of spacetime to multiverses without number, from false vacuums threatening annihilation to timeless frameworks where seconds do not exist. Each theory attempts to tame the void, to render the collapse of equations into a deeper harmony, and yet none are proven. Each remains tentative, a vision glimpsed through mist. The void resists capture. It refuses to yield its secrets easily. Theories multiply, but the paradoxes remain. Black holes continue to threaten information. The Big Bang continues to hint at impossible beginnings. Dark energy continues to mock calculations with its unfathomable smallness. The void endures, not as absence, but as defiance. But perhaps that is the point. Science advances by reaching the edge of maps, by standing at the cliff where equations fail and daring to imagine what lies beyond. Each speculation is not an answer, but a beacon. Each theory is a signal that the journey is not over, that the void is not an end, but a horizon. And so humanity stands between fear and wonder. Fear that reality itself may elude capture. Wonder that the collapse of equations may lead to revolutions beyond imagination. In the silence of the void, new languages of science are being written. Theories are not certainties, they are seeds. Some will vanish, others will grow, and one day, perhaps, one will bloom into truth. Until then, the void where equations cease to work remains what it has always been, the frontier of knowledge, the place where imagination must step in when mathematics steps back. The void where equations falter is not a silent mystery left untouched. It is pursued relentlessly by the instruments of science, by telescopes that drink light from the edge of space, by detectors buried deep in ice, by supercolliders that smash matter into fragments smaller than imagination. If equations collapse at the edge of black holes or at the beginning of time, then it is into those shadows that science now turns its gaze. The most direct probes are the gravitational wave. Observatories LIGO in the United States, Virgo in Italy, Kagra in Japan. These colossal machines, stretching kilometers across the Earth, listen not for light but for tremors in spacetime itself. When black holes collide, their event horizons merge and ring like struck bells. The ripples reach Earth as faint vibrations, displacements smaller than the width of a proton. By studying these waves, physicists hope to peer into the physics of collapse, into the hidden moment where relativity strains toward singularity. Some have even proposed that if black holes conceal wormholes or echoes of quantum gravity, those signatures might ride within the wave forms. Each detection becomes a test of whether Einstein's equations still hold, or whether they begin to unravel. Then there is the Event Horizon Telescope, a network of radio telescopes scattered across the globe, linked by atomic clocks to form a planet-sized eye. In 2019, it delivered the first image of a black hole's shadow, a ring of fire surrounding a darkness deeper than night. That shadow was not merely an image, it was a test. The brightness, the shape, the very size of the shadow measured whether relativity predicted reality correctly. Yet researchers are sharpening this instrument further, hoping to capture time-lapse movies of matter swirling, falling, vanishing into horizons. If deviations appear, if the shadows flicker in ways equations cannot describe, it may be the first direct glimpse of the void itself. In the cosmic background of the universe, other instruments search for the fingerprints of primordial collapse. Satellites such as COBE, WMAP, and Planck mapped the cosmic microwave background with exquisite precision. Their results confirmed inflation, the idea that the universe expanded faster than light in its first instant. But they also exposed anomalies, strange alignments, statistical oddities, whispers of something beyond the standard equations. Future missions like CMBs-4 and Light BRD seek even more delicate signatures, polarization patterns twisted by gravitational waves from the dawn of time. Should they be found, they would confirm that the universe carries scars of a pre-equation epoch, when space-time itself emerged from something deeper. But not all the tools gaze outward. Some probe inward into the quantum foundations of matter. At CERN's Large Hadron Collider, particles are accelerated too near the speed of light and smashed together, recreating conditions close to the first trillionth of a second after the Big Bang. Here, researchers study the Higgs field, quantum fluctuations, and the stability of the vacuum itself. If the Higgs boson hints that our universe is metastable, that its vacuum state may not be ultimate, then the void could be more fragile than we know. New colliders, even larger than the LHC, are being designed to push further, to test energies where unknown physics may emerge and reveal how equations might be rewritten. Other laboratories turn toward the quantum vacuum, that seething arena where even empty space is not truly empty. The Casimir effect, measured with plates separated by fractions of a millimeter, proves that virtual particles flicker in and out of existence, generating pressure without heat. These subtle experiments are not trivial curiosities. They test whether our equations of quantum fields are stable, or whether at some point infinities threaten again. The hope is that by mastering these fluctuations in controlled experiments, physicists may understand how they behave in the chaos of singularities. Even stranger are the quantum simulations. Experiments in Bose-Einstein condensation, gases cooled to billionths of a degree above absolute zero. In these systems, physicists mimic horizons, creating acoustic black holes where sound waves cannot escape. Here, some groups claim to have seen analogues of Hawking radiation, faint emissions resembling those predicted for evaporating black holes. If true, these laboratory models could be the first step toward confirming how equations bend or fail at horizons. Yet the frontier is not only experimental, it is also computational. The most powerful supercomputers on Earth now simulate the evolution of spacetime, collapsing stars, merging black holes, expanding universes. These simulations test not only Einstein's relativity, but candidate theories of quantum gravity. Does string theory predict stable black hole evaporation? Does loop quantum gravity permit bounces instead of singularities? Simulations can explore regimes no laboratory can reach, offering glimpses into conditions billions of years removed from human experience. Each run is a rehearsal of the void, a virtual exploration where mathematics still dares to venture, and still the void resists. For each new tool reveals more questions than answers. Dark energy, the mysterious force accelerating cosmic expansion, remains unmeasured in nature beyond its effect. Spacecraft like Euclid and the Roman Space Telescope are now tasked with mapping billions of galaxies, measuring how cosmic structure evolves, and testing whether dark energy behaves like Einstein's cosmological constant or something stranger. If its behavior deviates, it could signal new equations, pointing toward physics beyond relativity. There is also the search for naked singularities, forbidden in theory by the cosmic censorship conjecture, but not yet ruled out by nature. Should telescopes detect objects that defy horizons, or expose regions where space-time curvature is visible and unbounded, it would be the clearest sign that equations have collapsed in the open. Instruments now survey X-ray emissions, gravitational lensing, and high-energy bursts for such anomalies. The tools are not only technological, they are also philosophical, for each instrument measures not only the universe, but the limits of language itself. Scientists must decide whether infinities are physical or symbolic, whether they signal failure or truth. The tools test not only matter and energy, but the meaning of mathematics in describing the world. What emerges from this vast arsenal is not certainty, but direction. The instruments of science circle the void, pressing against its horizon, tightening the net. Each detection of a gravitational wave, each mapping of a cosmic microwave ripple, each collision in a particle accelerator is a probe question thrown into the abyss, awaiting an echo, and sometimes the silence of the void is itself an answer. No exotic deviation has yet appeared in gravitational waves. No wormhole echoes, no naked singularities. Perhaps the void hides itself more carefully than hoped, but even that absence is meaningful. It tells us how well equations work, how far they stretch, and precisely where they fail. The pursuit is endless. In the next decades, LISA, a space-based gravitational wave detector, will listen for whispers of supermassive black holes merging. Across billions of light years, pulsar timing arrays will seek the background hum of waves from inflation itself. New colliders may expose hidden particles or fields that change how space-time is understood. And all the while, the void will be waiting unchanged, patient, demanding deeper questions. Science does not fear such silence, it thrives on it. The void where equations cease to work is not the grave of knowledge, but its birthplace. The instruments of humanity, mirrors of glass, lasers in ice, magnets beneath mountains, extensions of a deeper will, the refusal to accept collapse as the end. Each tool is a hand reaching into darkness, searching for the next law, the next equation, the next revelation. The void will not be solved by one telescope, one detector, one theory. It may take centuries, perhaps millennia, but each tool brings us closer. Each observation sharpens the boundary where equations blur. And one day, perhaps, a signal will arrive, pattern in gravitational waves, a ripple in the microwave sky, a particle from the collider that will show how the void resolves. Until then, the instruments hum, lasers, fire, data streams, and the universe, vast and unyielding, continues to answer in whispers. In the beginning, humanity believed the cosmos to be chaos. Lightning was the anger of gods. The night sky was a canvas of myths. But then, equations appeared, lines of symbols etched by Newton, Einstein, and generations who followed. For centuries, mathematics seemed to reveal not merely patterns, but the very bones of reality. Equations explained the falling apple, the turning planet, the bending light. They guided spacecraft to the moon, predicted eclipses, and charted the invisible pull of galaxies. They were more than tools. They were promises that reality could be known, measured, written, and yet, at the very heart of existence, there lies resistance. Black holes, singularities, the Big Bang, places where equations stretch to infinity and collapse into silence. These are not just puzzles of science. They are philosophical thresholds, cracks in the mirror we hold against the universe. They whisper a terrifying possibility that the language we trust to understand reality may itself be incomplete. If the universe is a book written in mathematics, then the void where equations cease to work is a missing page ripped from the manuscript, forever unreadable. But perhaps the void is not absence. Perhaps it is invitation. For every time humanity has faced such silence, new insight has followed. Newton's laws collapsed at the speed of light. Relativity rose in their place. Classical certainty shattered at the quantum scale. Quantum mechanics emerged. Each collapse was not an ending, but a threshold. Perhaps the singularities are the next threshold, the next revolution waiting. But deeper still lies the philosophical question: why do equations work at all? Why should human scribbles of symbols mirror the behavior of galaxies, of atoms, of space and time? The physicist Eugene Wigner once called it the unreasonable effectiveness of mathematics. Why unreasonable? Because there is no necessity that reality should obey laws describable in numbers. Yet it doesn't till it doesn't dot in the void. We meet that limit. It is as if the cosmos speaks mathematics fluently, but at certain depths. It changes tongue. The language becomes unfamiliar, unfinished. Equations diverge, not because reality ends, but because our words do. Here lies a haunting thought. Perhaps infinity is not a feature of nature, but a reflection of ignorance. Perhaps singularities are the shadows cast by our incomplete understanding. Where equations explode into infinity, reality may be calm, governed by laws we have not yet written. For some, this realization inspires dread. If equations cannot follow, then human comprehension may be forever bound. The universe may harbor truths beyond reach, structures no mathematics can touch. To dwell on this possibility is to confront fragility. We are finite beings, wielding finite language, staring into an infinite cosmos. But there is another way to see it. The failure of equations may not signal the end of knowledge, but the beginning of a deeper form. Just as fire consumes itself to reveal ash, so do equations burn out, leaving the soil fertile for the next growth. The void is not a wallet, is a horizon. Even the question of time bends under this reflection. If singularities mark not beginnings but transitions, then perhaps the universe has no ultimate origin. Roger Penrose imagines cycles, each universe born from the ashes of another. Others suggest that time itself is emergent, a construct built from entanglement or entropy. If so, the clock of existence may be older than creation, ticking not in seconds but in transformations of being. What does this mean for humanity? On one hand, it humbles us. The neatness of equations was a comfort. To know that they collapse is to realize that certainty is an illusion. Reality is stranger, deeper, and less domesticated than we hoped. On the other hand, it ennobles us. For to confront the void, to walk willingly toward the edge of knowledge, is the essence of being human. We are creatures who seek not only survival, but understanding there is also beauty in the collapse. Equations work astonishingly well until they don't. And in that failure lies proof that we have reached the frontier. The edge of a map is not a defeat. It is an invitation to sail. To look at a black hole, to imagine the instant of creation, is to glimpse the unfinished manuscript of reality. Perhaps the void teaches that reality is not a closed system, not a solved equation, but a living process. Equations are tools, reflections, approximations, but never the thing itself. The thing itself is deeper. It is the cosmos unfolding, a symphony of structures that no single language can exhaust. The philosopher Wittgenstein once wrote, "Whereof one cannot speak, thereof one must be silent." But in science, silence is not resignation, it is patience. Equations cease to work, yes, but that silence compels us to invent, to imagine, to try again. The next revolution may already be written in data streaming from gravitational wave detectors, from cosmic maps, from colliders humming beneath the earth. The silence is temporary, and even if the void resists forever, there is meaning in the attempt. To write equations that collapse against infinity is to press symbols against the face of mystery, to show that humanity has reached for the deepest truths. Our failure is proof of our ambition. In this light, the void becomes sacred. It is the threshold where knowledge bows before mystery, where arrogance dissolves into wonder. To stand at the place where equations cease to work is to stand at the very edge of comprehension, gazing into the abyss that gave birth to time, matter, and stars, and perhaps beyond that abyss, there is no equation at all, only reality itself. Pure, unfiltered, unknowable. Yet even here, humanity continues. Equations may falter, but imagination does not. Curiosity does not. The desire to know burns brighter than any black hole, stronger than any collapse. It is the fire that refuses extinction. So the void is not the end of the story. It is the beginning of the next one. The collapse of equations is the seed of the next language, the next law, the next way of seeing. Science will return again and again, with sharper tools, with deeper questions, until even the void yields. And if it never does, then the mystery itself becomes the gift. To live in a universe where equations fail is to live in a universe alive, with wonder forever beyond capture, forever worth exploring. In the final image, imagine the night sky. Stars glimmer, galaxies drift, black holes spin in silence. Somewhere, equations guide their motion perfectly, And somewhere else, at horizons, at singularities, they collapse. But even here, in the failure, beauty abides. For the void where equations cease to work is not emptiness. It is possibility. It is the place where the next vision of reality waits. Patient, unseen, like a star beneath the horizon, preparing to rise.